A very good morning all of you. Today we will discuss about an important topic in biochemistry, that is heme catabolism. In heme catabolism we will discuss about synthesis of bilirubin and degradation of bilirubin. The hemoglobin degradation, it especially occurs in the reticuloendothelial system of liver, spleen and bone marrow. And this is specially occurs in the macrophages. What happens in the macrophages after the RBC hemolysis or after the degradation or completion of lifespan of RBC, there is release of hemoglobin. So this occurs in the macrophages. In macrophages, this hemoglobin is broken down into heme and globin. And this globin is converted into individual amino acids and again reutilized for the synthesis of hemoglobin. Now heme, there is enzyme, special enzyme, that is name is heme oxygenase. This heme oxygenase, it is an NADPH dependent enzyme. It requires molecular oxygen, and in this reaction there is release of iron from the heme in the form of ferric ions, and there is production of carbon monoxide. And this is the only reaction in which there is endogenous production of carbon monoxide occur. This is a very important MCQ. Heme oxygenase attacks the pyrrole ring, it attacks the methine bridge or methanyl bridge in between first and second pyrrole and cleave the pyrrole ring, converts the tetrapyrrole into the linear pyrrole molecule. So this one is the heme and this one is the alpha methine bridge or alpha methanyl bridge. There is incorporation of oxygen with the help of NADPH dependent heme oxygenase and cleave that methanyl bridge and convert this tetrapyrrole into the linear pyrrole molecule, and the name of this linear pyrrole molecule is biliverdin. This one is a green colored compound. This heme oxygenase, it is present in the microsome of macrophages. The second enzyme system, that is biliverdin reductase, this is again a NADPH dependent reaction. This biliverdin reductase converts that methine group, methine bridge into the methylene bridge. So here this methanyl bridge is converted into methylene of third and fourth pyrrole in the biliverdin molecule and converts it into the compound. The name of that compound is bilirubin. This one is a yellow colored compound and this is also known as unconjugated bilirubin. So bilirubin produced here in the macrophages, and this one is the cytosolic enzyme. So bilirubin, which is produced in the macrophages, it is known as unconjugated bilirubin. This bilirubin is toxic and it is less water soluble or not soluble in water and soluble in lipid. Not soluble in water and toxic. That's why it has to be removed from the body. So for that, it get transported into the blood and get bound to the albumin. Now coming to the transport of albumin, transport of bilirubin. This bilirubin which is produced in the macrophages is get attached to the albumin to form a albumin bilirubin complex. Because of this albumin, it get carried through the blood into the liver. Now this albumin, it has two binding sites. One is the high affinity binding site and another one is the low affinity binding site. So near about 25 milligram of bilirubin get bound to the high affinity site and remaining of the bilirubin get attached to the low affinity site and it get easily detached from that low affinity site and diffuse into the tissue in pathological conditions. So albumin binds to the bound to the bilirubin get transported to the liver. Now bilirubin metabolism, it is described in three important steps. The first one is the uptake of bilirubin by the hepatocytes. Second one is the conjugation, means conversion of this toxic unconjugated bilirubin into the conjugated one, and third one is the secretion into the bile. So these are the three important steps in the bilirubin metabolism. Now coming to the liver where bilirubin gets conjugated, the first step is uptake of bilirubin by the hepatocytes. This is the sinusoidal, this is endothelium, this is the sinusoidal surface of the hepatocytes. This one is the hepatocyte. Now once it get through this endothelium, the albumin get detached from the bilirubin. Albumin get detached from the bilirubin and bilirubin enters into the hepatocyte with the help of this specific transport that is known as facilitated diffusion. And it has very large capacity. Even in pathological condition, bilirubin uptake occurs in the hepatocyte without any doubt. So this is with the help of facilitated diffusion, and once it gets into the hepatocytes, there are two intracellular proteins. The first one is the ligandin and second one is the protein Y. This ligandin and protein Y, they prevent the backflow of bilirubin from hepatocyte to the blood, and also helps the bilirubin to be in solubilized form before it gets conjugated. So there are two important functions of these intracellular proteins. The first one is the ligandin and second one is the protein Y. They prevent the backflow or prevent the efflux of bilirubin towards the blood, and second, they keep the bilirubin in solubilized state before the conjugation. So these are the two important functions of ligandin and protein Y. So here the first step, uptake of bilirubin by the hepatocyte with the help of facilitated diffusion, and this is not a rate limiting step in the bilirubin metabolism. Even if there is more production of bilirubin, it get uptake by the hepatocyte for the conjugation. Now after the uptake by the hepatocyte, the second step is the conjugation. In conjugation, this toxic unconjugated bilirubin, it gets converted into the water soluble conjugated bilirubin. So this one is the unconjugated bilirubin So with the help of UDP glucuronil transferase, there is addition of one molecule of UDP glucuronate and converts this bilirubin into bilirubin monoglucuronide. Again, by the action of UDP glucuronate transferase and another molecule of UDP glucuronate, this bilirubin monoglucuronide is converted into bilirubin diglucuronide. And this one is the water soluble non-toxic bilirubin, and it can easily excreted from the body. That's why it is known as conjugated bilirubin or direct bilirubin. Now this conjugated bilirubin, that is bilirubin diglucuronide or conjugated bilirubin, there is this conjugated bilirubin gets secreted into the bile and enters into the intestine, but some part of this conjugated bilirubin get into the enterohepatic circulation, and with the help of MRP, multi-drug resistance protein 3, it gets back into the enterohepatic circulation, and again the uptake of bilirubin occurs via the hepatocyte with the help of these two proteins, that is OAT1B1 and OAT1B3, that is organic anion transporter protein 1B1 and organic anion transporter 1B3. With the help of these proteins, these conjugated bilirubin again taken by the hepatocytes. So mutation in these proteins, that is organic anion transporter protein 1B1 and organic anion transporter protein 1B3, leads to the disorder that is known as Rotor syndrome. Now starting with the hemoglobin is converted into heme and globin is converted into individual amino acid and again reutilized. While this heme is converted into biliverdin with the help of NADPase dependent heme oxygenase, and with the help of NADPase dependent biliverdin reductase, it is converted into bilirubin. This one is the yellow colored pigment. It is also known as unconjugated bilirubin. As it insoluble in water and toxic compound get attached to the albumin and transported through the blood into the hepatocytes. For bilirubin metabolism, it is described in three phases. First one is the uptake of bilirubin by the hepatocyte, second one is the conjugation, and third one is the secretion into the bile. So this is the sinusoidal surface where bilirubin get detached from the albumin, internalized into the hepatocyte with the help of facilitated diffusion. Then in hepatocyte, the conjugation occurs, in which unconjugated bilirubin with the help of UDP glucuronil transferase converted into bilirubin monoglucuride and again converted into bilirubin diglucuronide. This one is known as conjugated bilirubin. Now third phase in the metabolism is secretion of bilirubin into the bile. Before this secretion, it after the synthesis of conjugated bilirubin, some escapes and enters the portal circulation or enterohepatic circulation, and again there is reuptake of this conjugated bilirubin via the hepatocyte. For the reuptake of conjugated bilirubin into the hepatocyte, the proteins are required. They are known as organic anion transporter protein 1B and organic anion transporter protein 1B3. So defect in these proteins or mutation in these proteins which are responsible for reuptake of conjugated bilirubin by the hepatocytes leads to the disorder known as Rotor syndrome, which results in direct hyperbilirubinemia. Now coming to the third part of bilirubin metabolism, that is secretion of bilirubin into the bile. And after the synthesis of conjugated bilirubin, this conjugated bilirubin, there is uptake, secreted into the bile canaliculi, and this secretion into the bile canaliculi is the rate limiting step. This one is the rate limiting step in the bilirubin metabolism. This one is the very, very important step in bilirubin metabolism, and this is the only rate limiting step in the bilirubin metabolism, that is secretion into bile canaliculi. The secretion into bile canaliculi, it is with the help of active transport and with the help of protein. The name of that protein or transporter is MRP2, that is multi-drug resistance like protein 2, and mutation in this protein leads to the disorder known as Dubin-Johnson syndrome. Dubin-Johnson syndrome. So this is the rate limiting step, require active transport. The channel or protein is required is multi-drug resistance protein 2, and mutation in this protein lead to the disorder known as Dubin-Johnson syndrome. Now, as it enters into the bile, and through the bile it enters into the gastrointestinal tract, that is ileum and colon. By the action of bacterial enzyme, that is beta glucuronidase, this conjugated bilirubin, it get converted into urobilinogen, and this urobilinogen, 90% of urobilinogen, it get converted into or get oxidized into the stercobilinogen and excreted in the feces, and characteristic brown color of feces is due to the stercobilinogen. Now, small amount of urobilinogen enters the enterohepatic circulation, metabolized by the liver, and some part get into the kidney. This urobilinogen through the kidney, it get converted into urobili and excreted through the kidney, and characteristic yellow color of urine is due to the urobili. So this is all about bilirubin synthesis and degradation. Summarizing the all, hemoglobin is converted into heme and globin. Heme, by the action of heme oxygenase and biliverdin reductase, get converted into bilirubin. And this bilirubin is unconjugated one toxic compound, get bound to the albumin, transported through the blood into the liver hepatocyte. The uptake of bilirubin into the hepatocyte is by the facilitated diffusion. Then second, the conjugation occur with the help of UDP glucuronyl transferase. The complete absence of this enzyme, UDP glucuronyl transferase, known as lead to the disorder known as Crigler-Najjar syndrome 1, and partial deficiency lead to the disorder known as Crigler-Najjar syndrome 2. So conjugation of bilirubin occur in the hepatocyte, then it is secreted into the bile canaliculi. Through the bile canaliculi and biliary system, it enters into the intestine, where intestinal bacteria or intestinal flora or intestinal bacterial enzyme, that is beta glucuronidase, causes conversion of conjugated bilirubin into the urobilinogen. The 90% of urobilinogen get converted into stercobilinogen and excreted through the feces. Some part get reabsorbed via the enterohepatic circulation, enters into the kidney, and this urobilinogen converted into urobilin and excreted. So there are some important inherited disorders of bilirubin metabolism. The first one is the CJ Krigler-Najjar 1, in which there is complete deficiency of UDP glucuronil transferase. The CJ2, that is Krigler-Najjar 2, in which there is partial deficiency of UDP glucuronil transferase. Next one is the direct bilirubinemia. The two causes, that is the DR, direct bilirubinemia. First one is the Dubin-Johnson. It is due to the mutation in the MRP2, that is multidrug resistance protein 2, bilirubin into the biliary canaliculi, and mutation in this protein leads to the disorder known as Dubin-Johnson syndrome. And next one is the Rotor syndrome is due to the mutation in this, that is organic anion transporter 1B1 and 1B3. These are responsible for reuptake of conjugated bilirubin by the liver. So this is all about bilirubin metabolism, that is bilirubin synthesis and bilirubin degradation. Near about 6 gram of bilirubin, 6 gram of hemoglobin degraded per day, and 1 gram of bilirubin gives near about 35 milligram of bilirubin. So this is all for today. Thank you all of you. Keep watching. Thank you.